Well, if we're going to find and justify horizontal and vertical asymptotes for these functions, we don't want to just be doing, hey, this limit does not exist due to unbounded growth. So the first thing, and you don't need to write this, maybe I will. The first thing we should notice is x cannot be 0, at least in terms of graphing f. And so 0 is the only place f might have a vertical asymptote. So that means the first thing we're going to do is do the limit as x approaches 0 from each side. Now I could write x minus 1 over x, but I'm given a name f, and so I'm just going to write f. Those mean the same thing. And so, it's hard to explain what's going on in my head without writing. So maybe I'll do, me down here thinking. So you can see what I'm thinking a little bit. Okay, so if I'm doing a number a little bit less than 0, like what? Negative 0.1, that would be negative 0.1 minus 1, negative 1.1, over negative 0.1, which is actually positive 11. When x equals negative 0.01, in the numerator, we would get negative 1.01, right? Negative x equals negative 0.1, x equals negative 0.01, right? Over negative 0.01 gives me, what is that? 101. And then x equals negative 0.001 minus 1 is negative 1.001 over another negative 0.001 gives me 1001. To me, that's pretty obvious that the limit as x approaches 0 from the left is infinity. That's going to grow. All those numbers are positive. Let's make it more pretty. The actual name for that symbol, or at least one of them, is a lemniscate, but whatever. Okay, so let me get a different color here. If we're going to do the limit as x approaches 0 from the right-hand side of f, I'm already leaning towards negative infinity. So if I did x equals 0.1, positive 0.01, positive 0.001, and again, I'm imagining this because I don't really have to do any work. I don't need to be precise, but if you can't follow what I'm thinking, let's write it out. So positive 0.1 minus 1 is negative 0.9 over 0.1, and that's going to be negative 9. When x equals positive 0.01, minus 1 is negative 0.99 divided by positive 0.01 is negative 99. And positive 0.001 minus 1, because again, I'm putting all of these into f way back here, in case you're curious. Right, that's going to be negative 0.999 over positive 0.001, negative 999. Okay, and so what do I get? I get negative infinity. I don't want to write limit does not exist due to unbounded growth because our job is to figure out how this function is behaving. Okay, now x equals 0 is the only place f is undefined, so we don't have to worry about asymptotes anywhere else, or at least vertical asymptotes. So the next kind of asymptote we look for, or horizontal, maybe we should summarize. So f of x has a horizontal asymptote, and that is x equals 0. So the y-axis is going to be an asymptote. Okay, so now let's do horizontal asymptotes. And to find a horizontal asymptote, or maybe to prove a horizontal asymptote, we're expected to do limit as x approaches infinity and the limit as x approaches negative infinity. Maybe I won't write that yet. So when we do the limit as x approaches infinity, what we're supposed to imagine is, well, what goes on in x minus 1 over x? Well, here's the idea. 1,000,000 minus 1 is basically 1,000,000. Divided by 1,000,000 is about 1. 1,000,000,000 minus 1 over 1,000,000,000 is even closer to 1 because that minus 1 on a billion is less effective than when we subtracted 1 from a million. So even closer to 1. A trillion minus 1 is basically a trillion. The subtracting 1 does even less of an effect. And the limit as x approaches infinity of f of x is 1. So f, oh my gosh, gotta go back, has a vertical asymptote back here. F has a horizontal asymptote. Y equals 1. Now you're going to see the limit as x approaches negative infinity of f is also 1. Because negative a million minus 1 divided by negative a million, well, is at least positive. And negative a million minus 1, negative a million plus 1, negative a million, those are all basically the same size. Negative a billion minus 1 is close to negative a billion, barely makes a difference. Divided by negative a billion is even closer to 1. Negative 1 trillion minus 1 over negative 1 trillion, even closer to 1. Okay, so now let's draw a sketch. Can I move this over? All right, so we need 0 and x equals 1. 1, 2, negative 1, negative 2, 1, negative 1. Okay. So what do we want to put on here? Well, maybe I substitute in some more points. F of 1, I don't need to, but maybe it's useful to have points. F of 1 is 0 over 1. So that means our graph that we're trying to sketch here has an x-intercept of 1. F of negative 1 is going to be negative 2 over negative 1, so that's 2 up here. Maybe I should draw in some asymptotes. I'm not really a fan of it, drawing in the dashed lines, but, whatever. If you're using those dashed lines to explain what your graph looks like, I don't think you have enough. Okay. And so, let's see, no removable discontinuities. We're kind of good. Now, to me, kind of makes sense. X approaches 0 from the right of f, goes to negative infinity. That looks like this. That should look like x is approaching 0 from the right-hand side. The y values go to negative infinity. And let's see, to the right of this point 1, 0, the limit as x approaches infinity of f is 1. And does that make sense that those y values are less than 1? I think they do. Because remember, over here we were thinking like, pen stopped working. We were thinking, a million minus 1 over a million, that's going to be a number really close to 1, but less than 1, because the numerator is smaller than the denominator. And then what? A billion squared minus 1 over a billion, that's close to 1, but a little less than 1. Okay, got my pen back. Anyways, so to me, let's go to this other point. F of negative 1 is 2. And the limit as x approaches 0 from the left is positive infinity. Oh yeah, that actually makes a ton of sense. And the limit as x approaches negative infinity is going to be 1. There's my graph. Let's call it f of x. All right. G of x is kind of boring or not that useful. I assume if I do h of x, that should get us a little bit closer. So the first thing I'm going to do, again, we're trying to sketch. We're going to find all asymptotes. Maybe I'll find an x-intercept. I mean, maybe I do that first, right? H of 0 is 8 over 9. So we get a y-intercept. X-intercept, we kind of need some factorization. So if I factor out a 2 from the numerator, I'd be left with x squared minus 4. So no need to write that. We'll rewrite this as x minus 2, x plus 2. Over x minus 3 as a factor times x plus 3. Okay, so kind of like last time, x can't be 3, x can't be negative 3. Those are the places we're going to look for vertical asymptotes, infinite discontinuities, maybe a hole, maybe not. Okay. So we have a bunch of limits to evaluate. So let's think about this. Limit as x approaches, let's just do 3 first, 3 from the left of h. Well, I don't really have anything I can ignore, do I? So I guess something I'm thinking about, my equation h has an x minus 3 in the denominator and nothing in the numerator. So I'm actually expecting a positive or a negative infinity here. Okay. So here's what I'm imagining. 2 times what happens when we substitute in numbers less than 3? Well, a number a little less than 3 minus 2 is a number a little less than 1. I'll write that as 1 minus. I'm not doing this as work. It's just what I'm thinking because it's hard to follow. A number less than 3 plus 2 is a number a little less than 5. A number less than 3 minus 3 is a number a little less than negative 6. Or like, negative 6.1, things like that. And a little less than 3. Gosh darn it, that's wrong. That's going to be like a negative version of 0, just a little bit less than 0. And a number a little bit less than 3 plus 3 is a number a little bit less than 6. Okay, so I suppose the important thing to notice, doesn't really matter what these are, but, in the numerator, let's call that 10, and in the denominator, that's 0. So this has to be, the limit as x approaches 3 from the left of h, is going to be positive or negative infinity. And so really what we need to know is for a number a little less than 3, are each of these positive or negative? Now, 2 is nice. 2 is positive. A number less than 3, like 2.9 plus 2, that's positive. 2.9 plus 2 is positive. 2.9 minus 3 is negative. And 2.9 plus 3 is positive. So overall, we are going to get a negative number. So I'm just going to say negative infinity. So when I do the limit as x approaches 3 from the right of h, I'm kind of expecting to get positive infinity, but let's check. A number a little less than 3, so let's skip over that. When I substitute 3, I get 2 times 1 times 5 over 0 times 6. So because I get 0 in the denominator, already I'm thinking infinity. Okay? And so a number greater than 3, like 3.1, 3.01, 3.001, 2 is obviously positive. 3.1 minus 2 or whatever is going to be positive. 3.1 plus 2 is going to be positive. 3.01 minus 3 is still going to be positive, right? That's going to be like positive 0.1, positive 0.01, positive 0.001. And 3.1 plus 3 is positive. So we do indeed get positive infinity. All right, so x equals 3 is a horizontal asymptote of h. Limit as x approaches, what was our other candidate? Negative 3, and we'll go from the left first, of h, is going to be, well, we put negative 3 into this x minus 3. We're going to get 0 in the denominator. But notice we're not going to get a 0 in the numerator, so we already know positive or negative infinity. So again, we'll think 2 is positive, negative 3 minus 2 is negative, negative 3 plus 2 is negative, negative 3 minus 3 is negative, and the only one that is really going to change anything, a number a little less than negative 3, that's like negative 3.1. Negative 3.01, negative 3.001, and each of those minus 3, we still have a little bit of negative left over. So we're going to say positive infinity. Limit as x approaches negative 3 from the right of h, so things like 2.9, 2.99, 2.999. Again, we're going to get 0 in the denominator, so negative 3 minus 2 is negative. Negative 3 plus 2 is negative. Negative 3 minus 3 is negative. But now we have to be detailed. So that would be, if we're doing negative 3 from the right, negative 2.9, negative 2.99, negative 2.999, each of those plus 3 is going to give us like positive 0.1, positive 0.01, positive 0.001. So 2 negatives divided by a negative and a positive gives us a negative overall. So I'll go back and x equals 3 and x equals negative 3 are horizontal asymptotes of h of x. What about, gosh darn it, that's 2 in a row. I must be tired. Vertical. These are called vertical asymptotes. Okay. We need some horizontal asymptotes. Limit as x goes to infinity of h of x. Limit as x goes to negative infinity of h of x. It doesn't matter whether you use positive or negative a million, positive or negative a billion, positive or negative a trillion. Subtracting 8, subtracting 9 are so small, they become irrelevant. So we just focus on 2x squared over x squared. And so we're basically going to get 2 times a million squared over a million squared, 2 times a billion squared over a billion squared, 2 times a trillion squared over a trillion squared. And because we're squaring the inputs, I don't really bother thinking through with negative a million, negative a billion, negative a trillion. Square those and I get a positive. So either way, we get y equals 2. Y equals 2 is the horizontal asymptote of h of x. Okay, so let's sketch that. So let's see, 2, 3, okay, we need a little bit bigger graph. Oh man, that's y equals 2, huh? Okay, maybe some gray asymptotes. So let's see, that's x equals negative 3, x equals positive 3. I forgot, I was going to show what this looked like in Desmos. I'll do that here. And y equals 2. Okay, h of 0 is 8 over 9. And so, I don't know why, some people are always worried that our graph is going to cross an asymptote here between negative 3 and 3. You really don't have to worry about that. Remember, how do we get those horizontal asymptote, or that horizontal asymptote, y equals 2? Those x approaches infinity. We were thinking about a million, a billion. That's nowhere near 1, 2, or 0, so you don't have to worry about that. Okay, so let's see. Now suppose if I wasn't confident, I could substitute in 1. And let's see, h of 1, that's going to be 2 minus 8, which is negative 6, over 1 minus 9, so that's negative 8, so that's 3/4. Ooh, I hope the limit as x approaches 3 from the left goes to negative infinity. Ah, that's exactly what I wrote. Sweet. So that, oh, right. Okay. So something else you should remember from pre-calculus sort of stuff is how to find zeros of rational functions. And the quick, normally we'd set h equal to 0 and do some algebra. But, if you set h equal to 0, the first thing you're going to do is multiply by the denominator, in this case, the quantity x minus 3 and the quantity x plus 3. And you're just going to have 0 equals the numerator. So whatever numbers make the numerator equal to 0, in this case 2 and negative 2, those are going to be the x-intercepts. So again, I'm going to go here, and I assume, even without looking, the limit as x approaches negative 3 from the right of h should be negative infinity. And notice that's exactly what happens. Okay. And so the rest we can kind of fill in. The limit as x approaches negative 3 from the left is positive infinity, and the limit as x approaches negative infinity of f is 2. So we'll draw it that way. And then we kind of have a matchy-matchy bit over here. All right, let's see if we can pull up Desmos. Ooh, we don't want to bring those up. Okay, let's just do... Can we do new? No, we can't. One of these days I'll learn how to use a calculator. Computer. Here we go. Okay, Desmos. Okay, so what were we graphing? We were graphing 2x squared minus 8 over x squared minus 9. (2x squared minus 8 over x squared minus 9. So notice that's exactly what we had. So vertical asymptote, x equals -3. Vertical asymptote, x equals +3. This graph approaches 2 as x goes to positive and negative infinity. I suppose we could zoom out a little more for that. X intercepts at -2 and 2. I'm feeling pretty good about that.